Good morning, guys. Today we're going to start our work with arithmetic and geometric series. We've talked before about a sequence. A sequence is an ordered set of numbers, a set of numbers that we generate by repeating a pattern again and again and again. A series is where we take the numbers from that pattern or from that set of numbers and we add them all together. So it's the sum of the terms within a sequence. So if I want the sum of the terms in a sequence, I first need to identify is it arithmetic or geometric, and then is it finite or infinite, because there are different things going on. And just think about, and we've talked about in class where these formulas actually come from, but if we're just thinking conceptually about what's going on, if something is infinite, we're adding infinitely many numbers to it if there's an infinite set. So it seems like it would never, you would never be able to get a sum. So we first want to look and see if we have a finite or an infinite set. So in an arithmetic, because the numbers are always getting bigger and bigger and bigger in absolute value, because you're adding again and again and again, it has to be finite. So we can only do the sum of a finite arithmetic series. If it was infinite, obviously there is no sum to that because you're adding eventually either positive or negative infinity. We would never, it would never terminate. So first thing we're doing, identify if it's infinite or finite. So in this case, we're finding the sum of n terms, which is what S sub n represents, the sum of n terms. And then we have this formula, which is n over 2 times a1 plus an, where n is the number of terms in the series, number of things we're adding up. A1 is the first term in the series, and an is the nth term in the series. So pretty straightforward. It's just plug the numbers in to get that sum. So let's look at our two examples right here. We're going to find the sum of each finite arithmetic series. So if I have this term, or this series right here, it says find the sum of 10 terms. So S sub 10, and do we have to write the S sub 10? No, but just kind of humor me. Let's make it look mathematical. So sum of the first 10 terms is going to be the number of terms, which is 10, over 2, times the first term, which is 0.3, and the 10th term, which in this case is 0.30. Sorry. Got a couple of typos right there. Apologize for that. Found a good marker. Well, we'll have to do it in green. That should be 2.7 and 3.0. Because you can see the pattern was add 0.3 each time, so obviously I can't add 0.3 and then end back up at 0.3. So, first term, 10th term, and then just do your arithmetic. 5 times 3.3 is going to be 1516.5. Same thing I would get if I was to write out all 10 of these numbers and just add them up on the calculator. So it's just this formula will speed up that process for us. All right, let's look at this second example here. A little bit different in that we know we're adding up the first 100 terms. So this is one where it's obviously beneficial to use the formula because I don't want to generate this sequence for 100 terms and then have to add all those together. So the sum of the first 100 terms is going to be number of terms over 2 times the first term in the sequence, which is 15, plus the last term in the sequence. Well, we don't know what the last term in the sequence. This one it told us we stopped at 30. Or sorry, we stopped at 3. This one we don't know what the last term is. We don't know what the 100th term is. So we got to kind of pause a little bit and find the 100th term. Well, how do you find a specific term in an arithmetic sequence? You use the recursive formula, or the explicit formula rather. Explicit formula is meant to find specific terms based on their position. So my explicit formula is A1, which is 15, plus the pattern, which is minus 5, because we are subtracting 5 each time, times n minus 1. Remember your formula, A1 plus D times n minus 1. That's your AN. Well, we need 100th term, so 15 plus negative 5 times 100 minus 1. So we get 15 minus 5 times 99. 5 times 99 is 495. So 15 minus 495 should be negative 480. So that's our 100th term in that sequence. So if we were to write this out and subtract 5, subtract 5, subtract 5 again and again and again, 100 times, we would get negative 480. Now finish it off by doing the arithmetic. 50 times whatever 15 minus 480 is, so that's negative 465. And 50 times negative 465, you have to help me on that one, is negative 2,000, negative 20,000, negative 3,000, and negative 500. So negative 23,500, assuming my arithmetic is correct on that, is the sum of this finite arithmetic series. So it's really about recognizing that it's finite. The stops after 10 terms, stops after 100 terms, and that it's arithmetic. We are adding 0.3 each time, or we are subtracting 5 each time, and then you're just plugging in the numbers. If I'm missing a piece of information, then I'm going to use my recursive form, keep saying that, my explicit formula to generate whichever term I happen to not be given. And realistically, I could be given a series, and it could say start at the 6th term and add up all the way to the 15th term. That's always an option. So in our formula where it's A1, in that specific case, it'd be A6 plus A15. And we would be doing, if it's 6 to 15, that would be adding 10 terms together. So you've got to be a little flexible and know how this can actually relate to whatever the question happens to be asking. But that's, I don't know where I'm at. That's the sum of a finite arithmetic. Give me a second and I'll get the information about geometric series up here. Here we have the formula for sum of a finite geometric series. We looked at it in class the other day where this actually comes from. But again, we're first identifying that it is finite. The series is going to terminate. We're only going to add up a fixed number of terms instead of infinitely many terms. And it is geometric. We're multiplying by the same value, that common ratio, every single step in the production of this sequence. So that tells us it's geometric. And yes, it is possible to have an infinite geometric series, and we've talked about that in class already also, but we'll look at the formula and how to work some of those problems here in a minute. But first, let's focus on finite geometric series and the formula that we use to calculate it. So the sum of n terms is equal to the first term times 1 minus the common ratio raised to the number of terms in the series, all over 1 minus that same common ratio. Now for these, as far as the actual final answer, I'm okay with if y'all round them off to 3, 4 decimal places. If it terminates, just take it to however far it terminates. But if it doesn't seem to terminate, then go ahead and round it off 3 or 4 decimal places. And the reason is because we're dealing with ratios, or with these numbers and exponents, and we know that if n is the number of terms, if I'm adding up 100 terms, I've got an exponent of 100. We know because of exponentiation that when I'm multiplying a number again and again and again, the numbers are going to grow very, very quickly, typically, or get tiny. So we get some pretty ridiculous numbers when we sit there and try to do all the arithmetic on it. So as far as your answer goes, on these, I'm okay on all of your finite geometric series problems because we have the exponent on there, of punching them in and rounding it off to 3 or 4 decimal places. But if you want to do the arithmetic, simplify it down, there's nothing wrong with that either. Sometimes it's just as easy to do the actual arithmetic if the numbers are manageable. But let's look at the 2 examples we have here. I want to find the sum of each finite geometric series. So I have this series right here. So first thing I have to ask me is it finite? Well, I have 1, 2, 3, 4, 5, 6 terms, so okay. So 6 terms that I'm adding together, so I don't have the dot, dot, dot over there on the end. Then ask, is it geometric? So is the pattern a multiplication pattern? Well, you see we're getting cut in half every time. So it's times a half, times a half, times a half, and so on. So we're multiplying by a half every time. So yes, it's finite, yes, it's geometric, so we just use our finite geometric formula, which is a1, the first term, times 1 minus the common ratio, which is a half, raised to the number of terms, all over 1 minus that same common ratio. Now again, you can punch all that in the calculator right now if you want to. Be careful, make sure you're grouping appropriately. Group the 1/2 before you raise it to the 6. Group that entire denominator together, however you want to. This one's pretty easy to do by hand, it's not bad. So we get 1 minus 1 over 2 to the 6th over a half. So 2 to the 6th is 64. So 64 over 64 minus 1 over 64 is going to give me 63 over 64 over a half. So what's that, 63 over 32? When you do all the arithmetic on that, multiply by reciprocals and all that good stuff. So half of 63 over 64 is 63 over 32. Yeah. Sorry, divided by, half divided into 63 over 64. If you had punched all that in the calculator, you would get, what's it come out to be, 1.96875. So either one of those are acceptable answers in this case. This next one, we are just going to go to the calculator. I'm not going to try to do it because we're talking about powers of 10, so they get pretty outrageous. So first thing we're going to do, identify, is it finite? And yes, it's dot, 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 but they're telling me to stop at 10 terms. So we're going to find the sum of the first 10 terms. Is it geometric? Well, I know right now it should be geometric. It should be a multiplication problem because we're alternating signs right here. So if I'm going from negative to positive to negative to positive, that's because we're multiplying by some kind of negative number. Now, if that negative number is the same number every time, then yes, we're geometric. So negative 3 times something equals 9 halves. Well, that something would have to be negative 3 halves. Same thing right here, times negative 3 halves, because it's times negative 3 times positive 2. That's your common ratio. So we have a finite, we have a geometric, so we're going to go to our formula. So we're going to A1, first term, times 1 minus that common ratio, raised to the number of terms, which is 10, all over 1 minus the number of terms. Or sorry, 1 minus the common ratio. Again, this one, punch in the calculator, make sure you group your numerators, group your denominators, group your fractions, all that good stuff. You can calculate it piece by piece or all at once. Again, this one gets really ugly trying to deal with 3 to the 10th power and 2 to the 10th power and all that stuff. So you just punch that one in and it should give us approximately 67.988-ish. So that's it for sum of a finite geometric. It's just like the other one. We recognize that it's finite, that it's geometric. Then we go to the formula and just plug in the appropriate values. Give me a second, I'll get the sum of an infinite geometric series up here. Here we have the final series that we're going to talk about, and that's the infinite geometric series. Now, a geometric series can have a sum even if it's infinite, which is different from an arithmetic. An infinite arithmetic can never have a sum because we're adding eventually either positive or negative infinity, depending on which way we're counting. But in a geometric series, if we meet this one criteria right here that says absolute value of r is less than 1, okay? And absolute value just means that we're dealing with, the magnifier, whether we're making numbers. We don't care if they're positive or negative. We're talking about the growth rate. So our common ratio has to be less than 1. And what's the significance of what happens at 1? Well, at 1, we move from, if we're multiplying, because that's what r is, it's what we're multiplying by every time. Well, if we're multiplying by 1, the numbers don't change. But if we multiply by a number greater than 1, the numbers are being magnified. They're getting bigger and bigger and bigger every time. If we're multiplying by a number smaller than 1, or between 0 and 1, the numbers are actually getting smaller because you're multiplying by a fraction a portion of the original value. So if R was, say, a third, each next number is a third the size of the previous number. If we're multiplying by 3/4, each successive number is 3/4 of the following number. So the numbers are getting smaller and smaller and smaller and smaller and smaller. So what we can say is that if R is less than 1, the numbers are converging. They're coming to a smaller number. They're coming to a fine point. They're going to get very, very, very close to being 0 at some point, where if the numbers are bigger than 1, they diverge. They just keep growing and getting bigger and bigger and bigger, and they never actually come to that set point. So that's why, because these numbers get so tiny, as we've talked about where this formula came from, because the numbers get so tiny, because the growth rate, or because the common ratio is less than 1 or between 0 and 1, we can say that there is a sum of that infinite geometric, and the formula is first term divided by 1 minus that common ratio. So let's work a few examples where we find the sum of an infinite geometric. So we've got to go through, first off, is it finite or infinite? Yes, it's infinite. We can see our dot, dot, dot there on the end. Okay. Is it geometric? So we want to find our pattern. What are we multiplying by? Well, 1 times 1/3 is 1/3. Times 1/3 times 1/3, so that holds up. And then we have to ask ourselves, is that R between 0 and 1? That's what absolute value of R less than 1 means. Is this number between 0, is the absolute value of that number between 0 and 1? And yes, it is. So we meet the criteria to be able to use this formula. If it had been bigger than 1, say it had been multiplied by 3 every time, then we would just say not possible. There are no sum. And now we can say sum of infinite terms is equal to A1, the first term, over 1 minus that common ratio, which is 1/3. And then do the arithmetic. You don't need the calculator on these because we've taken the exponents and all that stuff out. So it's just 1 over 2/3, which is 1 times 3/2 or 3/2. So 1.5. Okay? Now, I want y'all to pause the lecture right here for a second. Try to take this infinite geometric and take this infinite, or see if it's an infinite, but find the sum of this series right here, and I'll wait while y'all work on that. Well, hopefully you've had enough time to finish that one. Let's see how you did. So, is it infinite? Yes. Is it geometric? Well, the signs are alternating, so that tells us we're at least multiplying by a negative. What negative are we multiplying by? Well, it looks like 2 over 3. And then times 2 over 3. Times 2 over 3. So we have it. And our R is less than 1. So it's infinite. It's geometric, and our R is less than 1. The absolute value of R is less than 1. So we can figure out the sum of that infinite is A1, which is first term, over 1 minus the common ratio, which is negative 2/3. Then we go through to the arithmetic. 4 over, that's 5/3, right? 3 plus 2 is 5. So it's 4 times 3/5, so 12/5. So there is the sum for that series. So if I was to take this and write it out 1,000,000 times, it would get very, very, very close to 12/5. And then I would write it out, if I wrote it out 1,000,000,000 times and added it up, it would get very, very close to 12/5. So eventually, I'm going to get so close to 12/5, I'm going to become 12/5. It's just going to keep repeating again and again and give you that same value that to infinitely many decimal places, it's going to look like 12/5. Okay, so we've got 3 formulas. We've got the finite arithmetic formula. We've got the finite geometric formula. We've got the infinite geometric formula to be able to calculate those three specific types of series. One last thing I want to talk about is just a way to kind of write a series in a little neater and cleaner format. So give me a second and I'll get all that information up here for you and we can wind up this lecture. Alright, so the last thing I want to talk to you guys about is a way to neatly write a series. It gets really annoying writing 3 plus 7 plus 11 plus 15 plus 19 or 3 plus 6 plus 12 plus dot dot dot. And so it gets annoying writing that again and again, or writing that I have this pattern going on and I want to add up the first 10 terms. We want a neat, clean way to do that. And the way we do that is with summation notation. It's also sometimes called sigma notation. You may see it in some texts referred to as sigma notation. And the reason is because it's got this big sigma, as you know or should know. Sigma is the Greek letter for S. We use it in a lot of different things in math. This capital sigma right here to us denotes that there's a sum, S for sum. So sigma notation, the way it's written out is you got a number on bottom, number on top, and then this expression over here. And the way we read that is we want the sum from this term to this term of this sequence. Pretty straightforward. So this A sub I right here is the explicit formula for that sequence. So this generates a list of numbers. This is telling me which chunk of the numbers we want to add up. So that's how summation notation is read and how we work through it. So this is just the first number in the sequence, and then this is the last number that I'm wanting to add up. Or sorry, first number in the series, meaning where I start adding. That's the last number in the series. It doesn't necessarily have to be the first number in the sequence. So let's write each of these in summation notation. So it's pretty straightforward. We know we're going to need a big old sigma on there. And we're going to need to have our starting position. Now, I'm using I. Some people will use a K, a J, and this variable really doesn't matter as long as we're consistent with whatever the variable is here. We need to have the same variable in our explicit formula. So I equals, and we just look at our numbers here. Well, starts with the first number. As far as we know, there's nothing else in front of it because there's no plus sign in front of it. So 3 is our first number, and how many numbers are there? 1, 2, 3, 4, 5. So we want to add the first 5 positions. Okay, we want to add the first number through the 5th number of this specific sequence. So we need to get this explicit formula that generates that sequence. So we go back to how we write an explicit formula. I first identify as an arithmetic or geometric. Well, I see my pattern is plus 4. So if plus 4 is my pattern, we know that we're going to do the arithmetic, which is the explicit for an arithmetic is A1, which is 3, plus the common difference times, which is 4, times n minus 1. Well, in this case, we're using I minus 1 because that's the variable that we've chosen. If you want to make that an n, because that's what we've been working with, then you can make that an n. It doesn't make any difference. So if I clean that up, the sum from term 1 to term 5 of 4i minus, what's that, 1? If I distribute 3 plus 4i minus 4, so 4i minus 1. So this right here would generate those 5 numbers, and that big sigma tells me once I've generated them to add them up. So we can read this the same way we read 3 plus 7 plus 11 plus 15 plus 19. All right, so that's the summation notation for that expression right there. Let me put it right here. Let's look at number 2. We want to do this one. First off, the number of terms. Obviously, we're starting with the first term because that's where it says to start because there's no pluses in front of it. So starting with the first term, and it says go to dot, dot, dot. Well, dot, dot, dot numerically is infinity. So we're going to add up infinitely many terms. Of course, it's not the greatest series to work with, but we'll talk about that in a second. So infinitely many terms of this series, and then we just identify what type of series is it. So we can write the explicit formula. Well, I noticed that 3 to 6 and 6 to 12 looks like a times 2. So 3 times 2, 6 times 2, so it is geometric. So how do we add up geometrics? Or sorry, how do we write the explicit for geometric? It's A1, which is the first term, times r, which is times 2, the common ratio, raised to n minus 1, or in this case, I minus 1. So this portion right here is the worst part, and it's just the explicit formulas that we worked with for the past couple of days. So if it's an arithmetic, you write explicit of that specific arithmetic. If it's geometric, write the explicit for that specific geometric. This stuff right here is telling us which term we're starting with and which term we're finishing with. And most of the time it's going to be 1, but occasionally you may get another value in there. And you have ways to kind of figure out what those are. We'll play around with some of those in class. This very last example, write the terms of the series. So let's work it backwards. Let's take this and figure out what this actually looks like. What numbers am I adding up? So this is my explicit formula, this 2i plus 1, and they want me to add the third term through the 7th term of that sequence. So pretty straightforward. I get a sub 3 by doing 2 times 3 plus 1. I get a sub 4 by doing 2 times 4 plus 1. A sub 5, 2 times 5 plus 1. A sub 6, 2 times 6 plus 1. And a sub 7, which is 2 times 7 plus 1. So the series would actually be 7 plus 9 plus 11 plus 13 plus 15. So this is the series that's represented by that expression right there. Not typically are we asked to take it from summation notation and say, hey, write out the series, but you could be. That's how you could approach it. What's more likely is that they may say evaluate. So where instead of write the terms of the series, it may say evaluate the series. And we don't want to do it by calculating each one and adding them up. We learned all these fancy techniques, let's use them. Okay, so I don't care what the individual numbers are right there. So if I'm going to evaluate this series, I need to know, is it finite or infinite? Well, it's finite. Is it arithmetic or geometric? Well, we know that the explicit formula for an arithmetic is a number times I, or a number times n, where the explicit for a geometric, n is in the exponent. So since I is not in the exponent, I is part of a base, then we know that this is going to be arithmetic. So because we're multiplying by I, therefore it's arithmetic. Because that is not infinity, therefore it's finite. And I don't know why I wrote finite. Right. It's finite. So we have a finite arithmetic. Well, how do we find the sum of a finite arithmetic? Well, how many terms are we adding up here? 5 of them, right? The third, the fourth, the fifth, the sixth, the seventh terms. So the sum of the first 5 terms, those look a lot alike, is going to be n over 2, 5 over 2, times a1, which is the first term, in the first term that we're adding up. In this case, it's the third term. So a3 plus a7. The third term through the 7th term is what we're adding. So a3 is going to be what we just calculated a second ago, 2 times 3 plus 1. a7 is going to be 2 times 7 plus 1. So we get 5 halves times 7 plus 15. 22 over 2 times 11. All that gives us the sum of the first 5 terms is 55. That's a lot of 5s and s's on the board. Okay, so that's the more likely thing, but that we need to be able to work in whether it's written out like this and finding a sum, or whether we want to take a sum and write it in a neat, clean format like summation notation, or they may give it to us in summation notation. We've got to decide, is it arithmetic, is it geometric, is it finite, is it infinite, and then apply and use the sequence and the explicit formula to be able to get all the pieces I need for that particular formula. Okay, a lot of stuff that I've kind of thrown at you here, but we will go over it and work with it more in class. But make sure you've got all those notes and just really start working on having those formulas down. And they're not difficult to memorize if you kind of think conceptually about when we went over where they came from and just how they relate to the specific sets. Summation notation looks freaky. It looks like Greek to me. Greek to me. Anyway, so it looks like it can be ugly and nasty, but it's really first term to last term and the explicit formula. So don't overcomplicate it. But again, we'll practice all this and work with it more in class, and I will see you in class tomorrow, guys.